All right, okay, let's get started. So today we're going to start talking about three-phase systems. So if you think about where we are in the class, so for the sort of last month or so, what we've been talking about was sort of generation technology, right? We talk about how to generate power from solar, from wind, from hydro. So now we're going to move away from, so this class we'll move away a little bit from the resource that we, sort of what kind of resource was used, to the more sort of electromechanical part of power systems, right? So if you think before, for wind and hydro, we said, oh, the air or the water would turn a turbine and that would generate power. So we're gonna get closer towards how exactly does turning a turbine generate power, and what's the consequence of the fact that we're generating power that way have on the way that the transmission system work. All right, so this class what we'll be doing is we'll talk about three-phase power, three-phase systems. So the plan going forward is we'll talk about three-phase, then we'll talk about synchronous generators, then we'll look at transformers, then we'll look at induction machines. So those are the topics for the rest of the course, or the main topics for the rest of the course, right? So you see why we start with three-phase systems. Because all of the generation, transformer, and sort of this machines technology, these are mostly three-phase. So there's a three. So we'll write this shorthand three-phase using sort of 3-B for three-phase. And we'll see why this is technology we use. What does that mean, right? And how do we sort of do calculation based on this, right? So we're going to go away from the resource that was used to now sort of electrically, how do you transmit this power, right? How do you transmit the power? So then if you look at AC voltage, right? So if you look at AC voltage, right? So we've been looking at AC power for a lot of this class. This is just a reminder, it's a sinusoid with some frequency. In this case, this is 2 pi. In our case, this is 2 pi times 60 hertz. So with some frequency and some amplitude. This is what we have for an AC sinusoid. So how do we generate this AC sinusoid, right? How do we talk about AC power. So how do you generate AC power? So it turns out generating AC power is quite simple, right? So the law behind AC power is quite simple. It's basically a straightforward application of Maxwell's equations. So the idea is you put a magnet, and you wrap some windings around it. And what you do is you turn the magnet. This is the rotor. You turn this magnet, and then because you're turning this magnet, what you generate is a rotating magnetic field. And this magnetic field creates an electric field. And this changing electric field shows up across your wires basically as a AC voltage. Okay, so this is the sort of simple idea of how to generate AC voltage. You have a magnet, you turn this magnet, this generates a changing magnetic field. This sets up a changing electric field, and that is voltage if it appears across wires. Okay. Any questions about this picture? Okay, so then this is our picture of generation. So when we talk about things turning a turbine, right, we're talking about turbine turning a generator. What happens is this gets turned, right? So a turbine turns this magnet. Basically, this is turned by a turbine. Right, so this is turned by a turbine. Okay, so we have let's say wind or hydro, we say turning turbine means you're just turning this turbine, right? The turbine turns this magnet then shows up. Then this magnet generates an electric field. Okay. So the speed of the turbine, right? So any guess of the speed of the turbine is? Right? Or the speed of how fast does the magnet turn in our generators?
Really fast.
So but in the North American electric power system, how fast, like we know the exact number. At what rotation speed does it turn?
60 hertz.
60 hertz, right? So as a fact that we have a 60 hertz system comes from that these are the things that's turning at 60 hertz, right? So this turns 60 hertz. Okay, so these are the things that's turning at 60 hertz. That's why we have a 60 hertz system. Okay. So then something to keep in mind is we won't get to this class, but we'll get to it when we talk about synchronous generators. Is we do not, there's reasons that we do not want to change the rotational speed of the generators by a lot, right? So this speed does change. You know, it goes from, let's say, 59.5 hertz to 60.5 hertz, goes up and down by, say, 0.5 hertz, but does not vary a lot. And this is the point we'll come back later when we talk about synchronous generators. But for now, in our mind, what we can think of as this generator turns at 60 hertz, and there's a fairly constant speed at 60 hertz. Okay, so these are big things, turning at 60 hertz. Because it's turning at 60 hertz, that's a reason we have a 60 hertz AC, right? So in Europe, this will turn at 50 hertz. Okay, so the machine, the frequency of the system is basically determined by the frequency of this turbines that's turning at 60 hertz. Okay, so we have these things that turns 60 hertz, and this generate AC power. Right, so this is also a reason why generating AC power is easy, right? So compared to, say, generating a DC power, right? You don't need to do much to generate AC power. All you need to do is basically somehow get a magnet, right? So either a permanent magnet or a other kind of magnets, and just turn it. Right? So you have some source of mechanical energy. As long as you can turn a turbine, this will generate AC power. So the field, the magnetic field rotates at 60 hertz. It's a sinusoid. So the electric field is so this is the, right? So electric field is a time derivative of magnetic field, but still that's still 60 hertz. It's still a sinusoid. And if you have two wires, right? So these are the windings, right? So these are the sort of the wires. So you have a wire coming. You have wires on the stator, and then what happens is this: if you look at the voltage across these wires, you see this AC voltage. Okay, so this is how generators work. As you turn it, you get AC voltage. So if you look at the diagram of a generator, right? So what does a generator looks like from the outside? Basically, if you look at the schematics of the generator, this is my generator. This can go to a load. Right, what I have is I have some AC power going to the load. Right, so this thing definitely works. The system definitely works, and it delivers some AC power to the load. But this is not quite how our system operates today. Okay, so if you look at our generators, we do not have only two wires coming out of the generator. It's actually, we don't have two wires coming out of the generator. So one challenge of this kind of system is if you look at these sort of three parts, right? We have the generation, we have the transmission, and we have load. What it's very expensive to build a generator. It's also very expensive to get transmission lines, right? So it's quite expensive to both build generation and build transmission lines. And then if I have a system that's simply like this, I have a generator with a line coming out of it with a return path going back, then what's limiting the total power I can transfer? Like if I build a system like this, what's cost money? Which of this part, so how much does transmission cost? I guess that's a better way to ask it. So let's say if I build a 1 mile of transmission line, how much money does it cost? Can we have a guess? So I go out and I want to build a mile transmission line. This is a very low number. So Daryl says in chat, 40,000. This is orders of magnitude too low. Any other guess? So 40,000 will not build you like this will build you like a meter of line, right? So this is normally in the ballpark of tens of millions of dollars. So transmission lines are really, really expensive. It's very hard to build them. Right. So I have to buy the land. I have to put up the poles. I have to put up lines. So building transmission lines are extremely challenging in the US. Let's be clear. So in the US, it's almost try to build a transmission. Okay, try to build a transmission line and see what happens. So this is the cost. This is factors of just the material cost of the line itself, the labor cost of putting the line up, and the cost of buying the land under the transmission line. Okay, so it costs a lot of money. So once you get it, let's say you're able to build, then you want to squeeze as much as possible out of this thing. Okay? You want to squeeze as much as possible out of this. But then this sort of single phase transmissions, right? So single phase transmission. So single phase transmission, meaning just sort of one line going forward, one line carrying current. This way it goes to the load and the current flows back, right? This is sort of the standard diagram we have. This is inefficient. So this is inefficient of lines. Okay. So I have two lines, right? I need to build two lines. So one carrying power, well, let's say one carrying current from the generator to the load. One gives the current return path going back to my generator. So this is not very efficient. So Alex has a question in the chat: is the cost for long distance transmission line, transmission in general? So the tens of millions of dollars is for high voltage lines, right? So the lines going from the substation to your home is relatively cheaper, but although not by that much, but it's cheaper still in the hundreds of thousands or $1 million per range. For the high voltage transmission lines, the lines you see, has a tower and things like that. That's for tens of millions of dollars per line. So, and if you want, if I want to build a high transmission line around Seattle or Bellevue, that's costs even a lot more than that. So that's why when you have the chance to build, you want to build efficiently. But this sort of single phase transmission is not efficient because I'm sort of wasting a line, right? In some sense, I have a line carrying some power going forward, but the other line just carries this return current. Okay, so this turns out is not a terribly efficient way to use transmission lines. And this was an issue even back in the days of Edison and Tesla. right? So Tesla was the guy who solved this issue, right? Was at that time the sort of the physical building line was very difficult, and at that time Tesla thought a way to squeeze more out of this system, right? As Tesla thought, instead of building a single phase transmission, Tesla had this idea of, let's build a three-phase line. Okay? Let's build a three-phase line. So what Tesla said is, hey, is there a way to transmit power or current such that I don't need a return path? So can I guess think of a way to say, here I'm carrying a current, right? This way. So I need a return path that carries this current back, right? This is a conservation of charge. So is there a way to somehow transmit current, but does not, where I don't need this return path? Is there a way to only transmit? Any ideas? Any suggestions? Let's say you're Tesla at that time, and right. So can I do it without a ground? Can I do it without a path that's going back? So you cannot directly put it into the graph. Okay, that's a very bad idea. It's a short. But is there a way to right? So this is your ground wire. This is your ground wire. Right, so is there a way to get rid of this wire? Is there a way to just have some wire all carrying current but no return wire? Any ideas? I think, right? So, and it's important to think about this being a AC system. So because we're sitting sinusoid, is there a way to still satisfy the conservation of charge, but not have a wire, not have a ground wire, or not have all the return paths? So what can you do when you have AC wave? Right. So the idea in China is correct, right? You want a phase shift to cause right? So you want to destructively interfere with this, right? You want to cause a return shift. You want a phase shift such that you can cancel things out, right? So of course you cannot have the same, phase on the same line, right? So the thing is, of course, you cannot, one line you can only have one sine wave. But the idea is, so it turns out a simple calculation will tell you, as it suffices if you have three lines. And what happens when you have three lines is you can phase shift each of them by 120 degrees. And this way, you can basically add things up such that they cancel each other out when you look at a cross-section plane, right? So let's say here I have a sine wave goes this way, sine wave goes like this. Then here what I want to do is I want to phase shift this a little bit. Okay, so I want to phase shift this, by 120 degrees. I want to still phase shift this by 120 degrees. It turns out when you sum all of this up, this all sums up to 0, identically 0. Okay, so we have three phase lines like this, you sum up across identically 0. So this says if I have a system that's basically having three lines all carrying power to, say, a load. So you need to be careful how the load works, but let's say you have three lines carrying power to a load. Then ideally, you do not need this return path, because if you do it this way, what happens is, so if you do it this way, there's a 0 current on this plane. Okay, there's 0 point on the plane. So this is equivalent to a system where you have this, and this. Okay? So you save wires, right? So you save wires. you say basically a set of wires, you can get away with a smaller number of space, there's a smaller space. Or if you want, you can double up on the land you bought. Instead of building one transmission line, you can build two. Right? So saving wires give you a lot of options. So this reduces cost dramatically and makes things a lot easier for everybody. Right? So this is almost all transmission lines we have today are these sort of three-phase lines. As you offset things and such that they will cancel out. Right? So conservation charge says, I cannot have a net charge. I cannot have a net charge change over a plane. This thing says if you just offset the three this way, you have zero sum current. So people have questions in the chat, right? So any question with a three-phase system?
I think I'm kind of confused with like the three lines going in. Like, is that the way they're doing it? Like,
yeah. So this course will cover how the load actually works, right? How do you have a three-phase load? But just think of some load that can take three lines. Any other question about three-phase? Okay, so I'll do the last check question. So it's correct that normally we have a force neutral wire. So for safety, you may have a force neutral wire running this way, right? Just in cases they're not exactly balanced, right? So sometimes you have a force neutral wire, sometimes you don't. But again, the force neutral wire does not have to have the same capacity as the three lines. You can get away with a much smaller wire. So these are the but if we have but sometimes we still have a force neutral wire for sort of safety reasons, right? So you could ground them both. You could ground them both if you want, or you have a force wire for reliability and safety. But the idea, so the three phase should be relatively balanced. So any return current, if there are any current imbalance, should be small. Any other questions about three phase? Okay, so a good question in the chat is why 3? Why not 4? Why not 20? Any ideas? Like, why not have a 4-phase, 5-phase, 6-phase system? Why just stop with 3?
I think it's gonna be like too much load that the load can handle for the 3 wires, because if 3 wire, we need like another wire to neutral it out.
No, it's not the load. The load doesn't care how many phase you have per se. It's not the load is fine. If you have a 20-phase thing, I can probably make the load be 20-phase. But we're getting there. So if you have 4-phase or higher, turns out the system gets increasingly complicated. And the system is too complicated. And the balancing things across 4 phases is very challenging. Okay, so 3-phase, we need to balance this, it's hard enough. 4-phase is very challenging. And you don't get much benefit when you have 4-phase. So you have a diminishing return of benefits for having more phase. Turns out 3-phase gets you what you want. The currents adds up to 0, and having more makes things a lot more complicated. And sort of the sort of benefit and cost trade-off doesn't really work out. So we have 3-phase. I would typically stop at 3. So you cannot have 2. 2 is a return wire. Right? So 2 is a return wire. You have to have at least 2. So, sorry, you have to have at least a return wire. Right? So you have at least 2 wires. So with 3, I can give you 3-phase, right? So that's sort of 3 is the next non-trivial thing we can do, right? There's 2-phase is not better than 3-phase. Okay, so this is our 3-phase. And so, for power purposes, for sort of this, we have 3. If some of you ever working things like microelectronics or working via SI, then you will see polyphase with like 10 phases. Okay, so multi-phase is definitely not something that only is about power engineering. In power, we stop at 3 because we have big things. And 3 is, enough trouble, right? It's sort of, it's complicated enough. But if you work for something like VLSI or microelectronics circuits, you'll see things with 10 phases easily. You'll see polyphase coverage. Okay, but the idea of having more phase is very useful. So in Tesla, basically thought of, let's just have 3 phase. Right. So as we go on for the rest of the class, basically everything is something Tesla has thought of. Tesla has a sort of I guess Tesla was sort of the engineer who didn't really want to explain the math behind it, or he may not have known the math behind it, but he came up with all the ideas we had. And a lot of people follow up with the math. So here we're going to do the calculations, right? But this is sort of the intuition Tesla had when he first designed this. As you have sine waves, they're being waves, they can destructively interfere with each other. In this case, can add up to 0. Okay. So generating this 3 phase is actually quite simple for us. Okay, so generate 3 phase is simple. If you have a generator, right? If you have a generator, you have a so we're gonna have the 3 phases. We have A phase, B phase, and C phase. Okay, right? So you could call them 1, 2, 3. We call them phase ABC. Right? There's nothing special about the naming convention. We just call them ABC. So the way to generate is quite easy. It's quite easy. Because remember, one turn of this rotor, of this magnet, creates one complete cycle, right? Creates one complete cycle of the sine wave. So the way you generate it, you want to separate things by 120 degrees, as you basically separate the phase by 120 degrees. So this is what you do. You turn this, you say this is 120 degrees apart, and this is 120 degrees apart. And you can generate 3 phase. You can generate 3 phase power out of this. And this also gives you some idea of complexity. If you have a big generator, it's sort of not easy getting sort of wires into it. Right? So 3 phase, you need this set of wires coming up. Right? So if you have more than 3 phase, also the wiring becomes complicated. Anyways, this is the 3 phase we have, 3 phase system we have. So if you separate out where the wires are, right, where the coils are by 120 degrees on the ring, then you get each of the sinusoid will be separated by 120 degrees. Right, so if you look at the 3-phase system, basically you have the A phase, right, the AA prime phase, the BB prime, the CC prime. And interestingly, they all add up to exactly 0. Okay, so this is identity. This says something like 1 plus 1, 120 plus 1 minus 120. And this is identically 0. Okay. Any questions about this generation of 3-phase? Okay, so this is the 3-phase power generation. Right? You have just put it in 3 sets of coils, make sure they're separate by 120 degrees. Right, so this is where normally when we make this kind of generators, we're very careful to say they're separate by 120. But then such that they'll add up to be 0. Okay, they add up to be exactly 0. And so this is the identity. If you want, you can use your calculator to show this. Right, so if you look at the wires comes out of this generator, right? So 3 wires comes out. 1 comes out the A phase, 1 comes out the B phase, 1 comes out the C phase. Then the idea, right? So now the question is, what do you do with the return path, right? What do you do with the coils, the opposite end of the coils, right? We don't want 3 wires coming out, right? We don't want 3 wires coming out of it because that loses the point. Right? Our point is, we don't want 6 wires come out of this generator. We want to save the number of wires we can use. So we want the small number of wires come out. So what do I do with this A prime, B prime, C prime? Any suggestions? Right, so this is no good, right? You don't want this. This misses the point of the three-phase system. So the idea is, right, don't do this, right? This is not efficient. We need to do this. We don't have to bother with three-phase. So what should I do with these wires? What do I do with the connection? If we know the voltages are three-phase balanced, right? We know the voltages are three-phase balanced. I don't want to use 6 wires. Any ideas on what we can do? With the prime wires? So we can ground them, right? One suggestion is ground them. Okay, so that's a good suggestion. So what does ground them mean is basically say, so I'm only going to draw the prime. So what ground them means is, let's just tie all these wires together and make it into a ground. Right? I don't have to transmit them. Right, so this is, I don't need to transmit them such that, right, so since they carry the current balance out anyway, I don't have to transmit them. So that's the idea of grounding them, right? That's kind of. Hollis' suggestion is connect to related ABC socket. So exactly how should we connect them? All right, so one suggestion is to say, right, so one suggestion is I should just take these and tie them together and ground them. So Hollis, what do you mean by connect them to the socket to cancel it out?
I think, well, since they have like 120 degrees like phase differences, so yeah, so probably A would have C would probably cancel A and B would probably cancel a phase like before. So we just connect to the to the last phases, like, which can cancel it out. So probably we are not going to worry about it anymore.
Close. This so right. So what do we mean is, right? So canceling in this setting is basically saying that, right? What I can do is I can connect them in pairs. So canceling means that I can connect them. So I can try to connect them in some pairs like this. Right? So I can connect some things like this, A to C together. I can connect these two internally. I can connect these two internally. This is actually will also work. Okay, so there's 2 ways to do it. One is you ground out them. Second is you connect them internally, right? So you don't connect, for example, A to A phase, but you connect A to C, B to A prime, and C to B prime. And this turns out will also work. Okay, so these are the 2 possible. Right? So these are the 2 possible strategies we can have, and we'll be going through them in detail. Right? So this can ground them, or we can, this sort of called the Y. For obvious reasons, we they look like a Y when you connect them all together. Or what we can do is we can have something called a delta connection. This goes from A to, connects A to C prime, B to A prime, and C to B prime. Okay, so this becomes so-called a delta connection, looks like a triangle. Okay, so both of these connections work, and we'll see why they work and do calculation work. So 3-phase for us is really understanding these connections, computing the voltage, current, and power out of all of these, and then looking at how load works. Okay, for three-phase. These are our connected sources. Right, so the first thing, right, so the easier of the two to work out is the delta connection. Sorry, the Y connection. So let's look at Y connection. So Y connection comes from the fact that you have three single-phase circuits. Okay? You have three single-phase circuits. Right, so we can draw them this way. What we can do is we can redraw them. Right? We can redraw them by sort of connecting the return paths closer to each other. So what we can do is we can draw A with a load, B with a load, and C with a load. So this comes from drawing them differently. So this is C, this is B, and this is A. Okay, so this is my ABC phase. And then recognizing this, right? So let's make a connection here. Okay, we're going to make a connection, meaning that we'll merge the wires together. Right, we'll merge the wires together. And we'll connect this phase to each other. So what we get is this was one load. Each phase has a load. But then the lines are all merged together into one return pass. Okay. Right, these are all merged together. So this has IA, IB, IC, and here I have IA plus IB plus IC equal to 0. So I can turn this thing into a ground. Right, so this is equivalent to a ground since it just has 0 current. Right, so the idea is I simply connect the connect the return paths together. I tie them together. The current all adds up to be 0. This acts like a ground point for us, right? There's no current flow. So then internally to the generator looks something like this, right? So you just have three wires coming out of it. And we can draw this equivalently in this form. It's basically I have a neutral, right? This is neutral is some common point of coupling. And I have it's as if I have three generators or three voltage sources, A, B, and C. Any questions with this picture? So go ahead.
For the picture, it doesn't look like the inner side it's connected to ground, but it's actually connected, right?
Yeah, so ground for us is a reference point. So what does ground mean? Ground means something that has, let's say, 0 as a reference voltage. So we're going to call this fictitious point ground because the current through that point is 0. So we're going to call this ground. So here in three phasors, okay, because they add up to 0, we're going to think of the addition of them to be the origin or ground. So this is the way we're going to think about it. Okay, so if it's exactly balanced, you don't need to connect ground to it because it wouldn't matter, right? The sum of it will be 0 anyways. Okay. So from a sort of phasor notation, as we have three phasors, the angles are offset by 120 degrees, add up to 0. So I'm going to treat this point, this N, to be neutral, right? This is the point that has 0 voltage. Right? Any questions? Okay, so by convention, right? So by convention, VAN, right? The A phase of this thing has angle 0. right? So by convention, we're going to pick the A phase to be angle 0 and B and C phase each offset by 120 degrees. Okay, so those are the three-phase circuits for us. All right, so this is our Y connected. This is Y connected. So the idea is quite simple, as you can sort of almost just treat each of them. You can almost treat each of them to be separate entities. Right? You can sort of, as long as you know there's a B and C phase, or there are two other phases, you can treat each phase almost as a separate entity. Okay. Then in delta, what we have is, as we said, we connect the phases together in this kind of sort of triangle formation. And then if you draw the electric diagram, right, you draw the diagram, what we have is, we have a generator that's A prime. This N is tied to B prime. This N is tied to C prime. And these two ends are tied together. So if you draw this out, if you roll this thing into a sort of better looking figure, what we'll have is we'll have a triangle with three things. This will be VCC prime. This will be VB prime, VAA prime. Okay. So this looks like a triangle for us. Okay. So this is A prime, C prime, C, B prime, and B. And you draw this angle, then what we have is the three vectors, the power vectors, as since A is referred to B, right? So this is VAB, this is VCA, these are the voltages we have, this is VBC. So this is point A, C, and B. All right, so this is another way to think of the voltage vectors we set up. Right, so if you look at across the two wires, you get some voltage. Right? So these are the VAB, VCA, and VBC voltages. Right, and again, just to summarize, we use three. Any questions? Okay, yeah, so we'll be doing a lot of calculations for this later. But now it's just to get an idea of the connection of wires. So of course, again, to summarize, we use three-phase. There's many reasons we use three-phase. Right? We can produce more power because we use a generator. We can get, turn one generator into three generators, right? We can transmit more power. We can start a motor. So we'll see this later, but you can start a motor easier. It's more redundancy, right? If one of the lines fails, you can still operate the other two lines as a single phase system, and so on. But then, so all these reasons makes the fact that all the transmission lines we have today, or the 99.999% of the lines we have today are three-phase. And well, you can see this by going out, just counting the number of lines in this. But basically, if you look at the number of lines we have, these are the three transmission lines we have. Okay. So these are the lines we have. If you look at some other transmission lines, these are again sort of the multiple sets of three-phase transmission lines. Right. So if you look at this picture, again, these are three parallel lines. Sorry, there's two parallel lines running parallel to each other. So 1, 2, 3, 1, 2, 3. Three parallel lines running in parallel with each other. These are three-phase lines we have out there in practice. Okay, so we have many, many different examples of three-phase systems. Any questions for these, for the transmission technology? The next time when you go out there, you look at a transmission tower, count the number of lines. It should come in sets of three. Okay, so if no questions, then let's take a break. When we come back, we'll get into all the formulas we have for three-phase lines. We'll be looking at a lot of formulas. Let's take our 10-minute break, come back at 3:27. We'll go into the formulas and how do we relate the per phase voltage to line-to-line voltage and things like that. Okay. All right, okay, so let's continue. So the thing with three-phase power is that there are many, so there's sort of different sets of voltages we can talk about. Okay. In particular, there are something called the phase voltage. Right? So this is the phase to ground voltage. And there is something called the line voltage, which is the voltage between different lines. Okay, so the math, there are a set of formula that relates each of these voltages. And the idea is, to write down the set of formula so we can convert when we want to talk about phase to ground voltage versus when we want to talk about line to line voltage. Okay, so these are things we want to talk about in the class. So if you talk about phase voltage, this is things like VA. These are called VAN, VBN, VCN. So this stands for line. Right, so there's two names for this. One is either called the phase voltage or it's called the line to neutral voltage. Okay, so then we'll write the phasor notation for these, right? So the line to neutral voltage is, right, so the phase A to neutral voltage is simply 0 degrees. Right? There's no, the angle is 0, it's taking as a reference. And the B phase is 10 minus 120 degrees, and the C phase is VC is V angle 120 degrees. Okay, so a very common question you see in the homework and in the final is, let's say, given VA, can you find VC, right? So do you know the relationship between them? Or given VB, can you find VC? Things like this. Okay, so this is a sort of common question we can have. Right. So this is the phase voltage. Now the interesting is line to line voltage. Right. So what is then the voltage between VA and B? Any idea how to compute this? Right, so I have a line. This is phase A. This is phase B. I want to compute this angle. Sorry, I want to compute this voltage. How do I compute this? Right, so this is VAN minus VBN. Right, so this is the line to neutral voltage of phase A minus the line to neutral voltage of phase B. Okay. So this is V angle 0 minus V angle minus 120 degrees. It turns out this is √3V angle 30 degrees. Okay. Any questions about this? All right, so this is just straightforward subtraction. You get the √3 comes out in front and the angle 30. Right. So this √3 becomes very important. Okay. So for three phase, almost every question comes down to, can you divide or multiply by the correct √3? Do you know where this √3 enters? Okay, so it's very important to remember this is the line to line voltage is √3 times higher than the line to neutral voltage. Okay, so this is an important factor to remember. But otherwise, sort of VBC, this is same as before. We have VBN minus VCN. This is V angle minus 120 minus V angle 120 degrees √3 V angle minus 90. And same as C, right? This is same as VCA. This is VCN minus VAN. √3 and voltage angle 150 degrees. Okay, so the line-to-line voltage, right? So line-to-line voltage √3 is √3 higher with a shift of 30 degrees. So this is a summary of calculations. Any questions about this? Okay, so this is a very important set of equations to remember, okay, or know how to find it when you're doing your homework and the final. This for three-phase will come up again and again. What is the magnitude, right? Where do you multiply by √3? What's the angle shift? This comes up quite a bit. So summary, right? So summary, so there's a standard assumption we make. Because when we talk about voltage, right? So in practice out there, we say, oh, this transmission line is, let's say, 100 kilovolts, right? So this voltage, this voltage quantities are all stated line to line. And so if you do a question, if the question does not explicitly state otherwise, the assumption is that voltages are line to line. The power is the total power carried by three phase. So why do you think the voltage is line to line? Why is that voltage are stay line to line? Why do we pick this convention? Right, so analytically, it seems line to neutral is easy. Right? We say, okay, there's phase A has a voltage of V and angle 0 degrees, and so on. But then why when we say in a problem this is 100 kilovolts, it's almost always line to line. So that's not exactly what the load sees, right? So depending on how we connect the load may see the phase voltage or the line-to-line voltage. Depends on the load is connected, right? So yes, right. So the reason we say line-to-line is this is the thing you can measure, because the neutral is in some sense in the generator, right? If you think where the neutral is somewhere in the generator, and if you go out and you look at a line, right? So if you look at the picture of the line, the only thing you can measure is the line-to-line voltage. You have access to two lines, and you can measure the voltage between them. You don't really know where, right? You don't really have access to the neutral if you're looking at the line, right? You may not know how the generator is even connected, right? You may not know whether the generator is, Y connected or delta connected, right? So all you see is you look at you see three lines. Okay? So the voltage you can measure is the line-to-line voltage. That's why we talk about line-to-line voltage, right? As a convention. Okay, so it's very important to remember the voltages are line-to-line. Right? I cannot. So every time in the final, people lose marks because they thought the voltage was line to neutral phase A. That's not what it is. When you see a voltage, if it doesn't say otherwise, it is line to line. Right? Just remember that. And we'll make your, so you don't want to lose this kind of sort of trivial grades, right? So let's just remember this convention. Any other questions with this? Voltages? Right, so basically come down to this table of formulas, right? All the questions. So let's, for example, let's do some calculations. Right, let's say VA as 240 angle 25 degrees. We want to compute VAB. Okay, so this is a very typical question we have. Right, so and the way we figure this out is you go to this table, you look at VAB, right, at this number. Okay. So then what we find is VAB as a vector. This is √3 times VA with increased angle of 30 degrees. So you put all this in, 240 angle 25, right? Multiply again by angle of 30 degrees. So this is for 15.7, angle 55 degrees.
Wouldn't it be? No, no.
Sorry?
Never mind.
Yeah, right. Okay, so this is the simple calculation, right? So you will have a lot of questions like this. Given VA, compute VAB, compute VBC, compute VCA. Given VAB, compute VC, things like this. So you have a lot of questions like this. Okay. So for this kind of questions, just think back, think what the voltage should be, think of what the angle, you add or subtract, and it's not sort of overly complicated, but just I'll look at the angle, make sure you're adding the angle in the right direction, make sure you multiply or dividing by √3. Okay, so this is just equations. Okay. So as we said, right, we look at this sort of line-to-line voltage as you don't care where your generator is, right? So a generator could be a delta connected generator. That's fine. You measure some line-to-line voltage. It could be a Y connected generator. It still doesn't matter. You can measure the line-to-line voltage, right? So from the transmission side is all you care is you have 3 transmission lines and they have some voltage between. Right? So that's what we have on the transmission side. On the generation side, right? So let's now think about the load side, right? So the question is, how do you connect the load, right? How will the load work? So we have a load as what you have as, let's first look at something called a Y-connected load. Right? So it's very similar to how the generation is connected. It's basically you have 3 loads and you tie them together. At one end of the load, you tie them together, and you get something called a Y-connected load. Right? So you can pretend that you have a Y-connected generator. You have this generator. And then you have the load, a Y-connected load. So we have each generator corresponding to a load. Right? We have a generator corresponding to a load. And each of the load is getting some current. Right? So any questions about this connection? Okay, so this is a Y load connection. Okay. So most of the loads we have is connecting Y. The reason is if you connect them in Y, what you can do is you can still have a ground wire. What we can do is you can still have a ground wire. This carries some neutral current. It's not very large, but if there's slight imbalance, this can still carry some neutral current through this ground wire. And we have each load has a load impedance Z, and each of this load have some voltage across it. Right? So the load voltage is equal to the phase voltage. The load current is equal to the line current. Right? So here is we need to make sure that all Z's are the same. Okay? We need to make sure all the Z's are the same. Right? We want things to be balanced. Right? Again, remember the only difference between the 3 phase is 120 degrees offset. Everything else should be exactly the same. So we want to make sure the load are balanced. So how do we do this in practice actually? Like how do we make sure the load are balanced? Right, so here I just draw all the Z's are the same. But in processing the load, where do we do this balancing? So I have a generator. So I can make a generator 3-phase very easily. I have 3 transmission lines coming through, and this powers a load. Right, so if you think to your home, right, so where does load balancing happen? Okay, so this load balancing, where we balance the load, for us, this often happens at a sort of substation or at a distribution system, feeder head, right? So each home may not be all that balanced. But when we design the distribution system, we want to make sure so each phase has roughly the same number of houses on it, or has the same roughly same number of load on it. And then during real time, we may do some switching to make sure these loads are balanced. Okay, so these may not necessarily correspond to something in your home. Right? Your light bulb is not a three-phase light bulb, it's single-phase load. But when it may represent a collection of load. That's when you aggregate them up, they're roughly equal to each other. So that's why we can treat them to be sort of similar in value. Okay, so this is a balanced, wise balanced load. So now let's see how we do some calculations based on this load. So let's do calculations. So for a balanced system, we have ZA equals ZB equals ZC equals to Z. The impedance are all exactly the same. So I have IA, the current is VA divided by ZA. This is V over Z. Right. So suppose this has angle 0, Z has angle theta. So this is I angle minus theta degrees. Then you can repeat the same calculation with IB. This you'll get I angle is 1 minus 120 minus theta degrees. IC is I angle 120 minus, right? So the same shift happens again, the same 120 degrees shift again. Okay? So everything's balanced, right? So here we have all the voltage and currents are identical except a 120 degrees phase shift. Okay, so they're all identical except 100 degrees out of phase. And the consequence with that is, right, so what I can do is I can just study one of the phase. Right? I can just study one of the phase. And by studying the single phase, it suffices tell me that everything happened, right? I know everything that happens in the system. Okay. So if if everything's balanced, I can just look at this equivalent picture. I don't need to consider all three phases individually because at the end of the day, I just got a 120 degrees angle offset. Okay. So often we just consider the single phase. So we have this sort of single phase equivalent representation. Okay. So, right, so again, the currents are balanced. So the net current is 0, right? So we don't need to, right? So what we can think of is these two are at the same potential, right? Because they have 0 voltage, 0 current. Right? So that we can pretend that's a ground node for us. Or often in practice, what we do is we actually ground these, right? So we need a little bit of grounding, we can connect them to Earth. But again, we want to make sure the system is roughly balanced such that there's very small current flowing to the ground. Right, so this is the Y-connected load, right? This is Y-connected load. And another type of connection for load we have is delta connected load. Okay. So delta connected load is exactly the same as a delta connected generator. Is again, you connect the load in a triangle. So this can happen when you don't have access to ground. Right? For some industrial applications, there's not an easy ground to talk about. So can you think of an application when you have no ground? So where do you find an application we have, relatively large power consumption but no ground? have no access to ground. I need to connect load in this sort of delta fashion. Any ideas? So what kind of application?
Airplane.
Right, so airplane or ships, right? So in a big airplane, like Boeing 787, or when you have a large ship like aircraft carrier, you have a lot of power generated, but you don't have a ground. There's nothing to access as a ground, so you can have a load this way. Okay? So you connect them in delta, right? So here I have a line current and I have a load current, right? So IA comes in and splits into different current going different load. So we want to do a sort of similar set of calculations to figure out what the voltage and current relationships are. Okay. So if you look at the delta connected source, so this is delta connected load. Then equivalently, we can have a delta connect source. And it's first easier to think of a delta connect source and delta connect load together. Okay, well, later we'll look at what happens when you mismatch the source and the load. But here, let's say, suppose a load and source are matched in type. So I have a delta connected source. Right, so I have this source, I have 3 lines coming out, and this connects to a delta connected load. Right, so I have IA, IB, and IC. I have currents coming out this way. So I have a transmission line current that's made up of phase current, right, in different phases. So I have a voltage across a load that's VAB, right? So my load, this Z, sees a voltage of VAB, right? And has a current of ICA. So let's do the calculation here. So if you look at the current through a load, right? If you look at the load current A to B, this is the voltage VAB divided by the load Z. Okay. So these are all complex numbers. So I have the voltage divided by load. Similarly, I have the B and C as the VBC divided by Z. Similarly, the C to A phase. Right? So these are all line to line. So the phase current equal to the line to line voltage divided by the impedance. Right. So then for a delta connect system, so this is again fairly simple, as you just have sort of all you need to do is to relay the current flow to the line to line flow. Right? You need to relay current flow line to line flow. So the way we do that is if you look at the transmission line current flow and the phase current flow, is you'll see that the line current flow is IA plus ICA, right? IAB is IA plus ICA. So IAB, this current, if you look at the Kirchhoff's current law at this node, this equals to IA coming in and ICA coming in. So this is our current relationship between the figures. Then if you rearrange this equation, what we have is IA. This is equal to IAB minus ICA. So this is what I have. If you plug this into the equation, IAB is, let's say, some current value, IAB, angle minus theta. So if IAB has this relationship, IAB angle minus theta, then what is ICA? If IAB has a magnitude and the angle of minus theta, then what is the angle of ICA? What's the angle of? Sorry. Yeah, go ahead.
Plus theta?
No, right? So remember, this is a changing phase, right? So if we look at A to B rotated by C to A, so what's the angle difference for all this kind of
120.
120, right? So for three phases, all 120. So here you shift ahead by 120. So you can subtract this. So the magnitude is always the same. The angle just goes off by changed by 120. So here, if you do this calculation, this is again √3 IAB angle minus. Okay, so exactly the same as before, as the current goes up by a factor of √3. Right, current goes up by a factor of √3. The angle shifts by angle of 30 degrees. Okay, so for a delta connected loads, the line current, right? So load voltage is equal to the line-to-line voltage, and the line current is greater than the load current by a factor of √3. Any questions with this calculations? Okay, so this is the, right, so all this is sort of just different ways of getting to a offset of √3, right? This is sort of mostly bookkeeping for us, but it's still important to talk about it because this is example Y, right? So this is as the line current IA is 30 degrees, is 30 angle minus 10 degrees, right? The reason we talk about line current is, again, when you look at the system, all you see is 3 transmission lines, right? So it's easy to measure the current on a line, right? So that's easy. Anywhere during the transmission line, we can measure the current flow. But getting the current, getting the load current may not be so easy. So it's good to measure the line current and then by calculation, figure out what IAB is. Right? So much easier to measure the line current than the load current. And then it's much easier to measure the line-to-line voltage, right, in all kinds of systems. Okay, so that's why we talk about line current and line-to-line voltage. So here, if you do the conversion, this is IAB. If you look at the equation, this IA divided by √3, angle 30 degrees. So this is plugging the numbers, we get 17.32, angle 20 degrees. Any questions? Okay, so this is sort of the, if you have delta to delta or Y to Y, it is easy. Sort of the trickier question is, what if things are mismatched, right? What if I have, let's say, a delta source, but a Y load? Or what if I have a Y source, but a delta load? Okay. So here we want still to do simple calculations, right? We don't want to go in and do, work from first principles. So any ideas of what to do when you have this type of system? Say your source is delta, but your load is, say, Y. Any ideas? What is the easy trick here?
Is there any way to convert the load to also to delta?
Right. So the easy trick here is a load conversion, right? You want something called a Y delta conversion. Basically, if I give you a Y load, there is an equivalent delta load, it looks like. If I give you a delta load, there is an equivalent Y load. Okay, so this is the conversion we have. And the math is actually quite simple. The math is very simple in this kind of load. Right? So the reason we can do a conversion is basically saying, look, right, if my load is delta, I can look through the A to B port. I'll get something. If my load is, so this is a Y, so this is a Y connection. This is a delta connection. If the load is delta connection, I look through the A to B port. I will see something. Okay. Right. So here, so the question is, if the load is Y and I look through ZAB, what do I see? What is the equivalent resistance I see? What is the equivalent impedance? If it's Y connected, but I look through this A to B terminal, what impedance do I see? Any ideas for Y? Any guesses? Right, so this is just 2zy, right? So this is 2zy. Okay, so basically, right? So what do you see, right? If you flow a current through this, you see one zy this way, continues, you see another zy, this goes up. Okay? So you see two of them, you see 2zy. Okay. Any questions about this? Okay. So I see two of them.
But wouldn't be that connected to another zy at the left, which
no, C doesn't matter, right? C is not connected to anything. So we can ignore the third zy. Right? So I have two of them.
okay.
The third one doesn't matter. I don't see it. There's no wire attached to it, right? I'm not looking through C. So here I have ZAB. So this is maybe easier for us to conceptually think about. This is one Z delta in parallel with two of them, right? I have one load in parallel with two of them. So you can do this computation of 2 or 3 Z delta. Okay. So if you combine them together, right? So if you combine them together, if ZAB, right? So if you equate these two, right? If these two are equal, right? So if these two are equal to each other, what you get is 2zy equal to 2/3 Z delta, or zy is 1/3 Z delta. Okay? So this says a Y connected load is equivalent to a delta connected load if zy is 1/3 Z delta. Right? So this if and only if relationship. Right? So this is a way to convert the load types. Okay? This is a way to convert load types. Right? Any questions about this load conversion? Okay, and this load conversion makes our life really simple, right? Because let's say you have a question like this, right? This says, okay, compute the line current IA in this system. So each of my phase voltage is 120 volts. I give some value for Z. I want to compute this transmission line current. So one way to do this is do this from first principles. And one way to do this is do it from my first principles. By first principles, we can look at the following, right? So first principles. This is compute IAB, then convert to IA, right? So what I can do is I can say IAB, this is VAB divided by Z. So VAB is √3 VA angle 30 degrees divided by Z. This turns out to be 41.57 angle -7 degrees amps. Then IA is √3 IAB angle -30 degrees. You plug everything in. This is 72 angle -37 degrees amps. So this is the first principle way of doing this. as you match phase to phase, line to line current, and you just compute everything, right? You compute everything, and you see fact that you can convert from line to line and phase by a factor of √3 and angle 30 degrees. An easier way to do this is to say, well, this is an equivalent Y load. Right? I don't need to, let me first convert this to a Y load. So the Y, right, is the delta over 3. This is 1.67 angle 37 degrees ohms. Okay, I can convert this to a Y load. Then my calculation becomes very easy. This is IA as VAN over ZY, 120, 1.67 angle 37 degrees, 72 angle minus 37 degrees. Okay, so both ways, I can do it both ways, but in general, converting the load to match the generation is much easier. It's much easier. All right, any questions? Okay. Right, so this is easier. And really the point of this kind of conversion is when you have a mixed system like this. Okay, so for if it's just one generator connect to one load, you may be able to brute force it. Right? You can just go from first principle, figure out everything. But when you have two loads like this in the system, then you really do not want to figure out what each of the currents are and do first principle calculations. So when you have three things connected, then it's really much easier to do a transformation. Okay, so it's really much easier to do a transformation. Right? So here, let's say I still want to compute the current on this line, but now I have a Y connected load and the delta connected load. So really the first thing is to convert this to a delta to Y transformation. Okay. So the thing we want to do is to convert everything to a delta to a Y connected system. And I want this thing to be also to be Y connected, right? So here is, so for this, if my Z delta is 12 minus J9 ohms, then ZY is the delta divided by 3, 4 minus J3 ohms. Okay. All right. So and then if I have a system, if I have a two loads like this, are they connecting in series or are they connecting in parallel?
Parallel.
Right, so they're connecting parallel. Right? Important thing to remember is these are connecting parallel. These are not in series, right? So these are sort of two different loads parallel. So since they're connecting parallel, I have a equivalent impedance, right? I can compute Z1 equivalent with Z2Y. So this is for plus 3J ohms, parallel is for minus 3 ohms. Right. And then our circuit becomes very easy. This is 25 over 8 ohms. So all I need to consider is this equivalent circuit. And then IA is really simple to find, 120 over 25 over 8. This is 38.4 amps. Okay, so when you have two loads together, it's generally much easier to convert them into the same type as a generator and do calculation that way, rather than try and go in and figure out exactly figuring out what exactly the currents are. Okay. Any questions for this conversion? Okay, so in in practice, of course, you will have also the generators, right? Different types in one system. For us, we will not have that. For us, we'll stay most with one generator and multiple different types of loads. So there is always a clear idea of what to convert to. Right? So if your generator is delta, convert all loads to delta. Your generator is y, convert all loads to y. Okay, so the last part of the topic is power calculation, right? So we did a lot of voltage and current calculation. Now let's do the power calculation for three-phase. So this is just sort of rewriting the single-phase system, right? So complex power is VI conjugate, and we have real and reactive power. So what does that show up in three-phase? Right? What does that show up in three-phase? So in three-phase, we still have this, right? We still have for each of the phase, with V phase times I phase times the cosine theta for P, V phase, I phase, sine theta for Q. So it's always 3 times the phase power. Right? So this is always true. The tricky thing is, right? What does V phase, right? So what exactly do V and I phase mean? Okay, so we need to be clear about what V phase and I phase means. Okay, we need to be clear what, right? So three phase is 3 single phase systems. So it's 3 times the power you get from a single phase system. But it means, right? But we have 2 connections, right? We have Y and delta. So let's see whether the equations make sense for Y and delta systems. So let's say for a Y system, right? Let's say for a delta connect system, Okay. So here the phase voltage is VAB, the phase current is IAB, right? And the line to line voltage is VAB, the line current this is IA, this is √3 times IAB. So if you write power as 3 phase I phase cosine theta, then power is also equal to 3 VAB IA cosine theta. So this is the equation we want at the end of the day. Okay, power is √3 times the line to line voltage times the phase current, right? So this is what power is. Okay, so most time we write power notation as the line to line voltage and the line current. Okay, the line to line voltage, the line current. So there is a factor of √3 in front of this. Okay, there is always a factor of √3 in front of this. Right? Okay. And this again comes from the fact that given a transmission system, right, I can measure the line to line voltage, I can measure the line current. So I want to express the power in terms of quantities I can measure. Right? So I can measure the A to B voltage and the IA current. So this is my power equation.
Wait, how do you get √3 when there's 3 in it? Wouldn't it be
Okay.
3?
No. So I phase, right? So look at, right. So let's look at this equation. This is 3 VAB. Right? Times IA over √3 cosine theta. Because IA is 3 times IAB. So IAB is IA over √3. So I have a √3 at the bottom, so this √3 cancels, and then VA. So divide this into 3 IA cosine theta. So this is the power term. Right? So this is a root 3. There's a root 3 in front, not a 3 in front. All right, so this happens, this holds the same for reactive power as well. Right, so Q turns out will also be root 3 VAB IA sine theta. Okay, so it's always ways to compute the power. You can always convert things to line-to-line voltage and a line current. Line-to-line voltage, a line current. So for a Y-connected system, this is the same picture, right? I have P as 3 times the phase, I phase cosine theta, for V phase is 3 times, right? So this is VAB over root 3. Recall that V phase is VA, this is VAB over root 3. Right? So this is another root 3 IA cosine theta. So this is again root 3 VAB IA cosine theta. Okay, so the equations are consistent, right, as we expect them to be. You cannot magically get more power by converting, say, a Y to delta. Right? You cannot get more power by changing the model of this. Right? So this is some same thing for Q. This is root 3 VAB IA sine theta. Right, so it's always the root 3 sits in front. And then we have the line-to-line voltage times the line current times the angle difference to get P and Q for 3-phase. So this is something important to remember for us. So we'll stop here today. The next time we'll pick up from here, we'll sort of remind ourselves this is the power calculations. And then we'll go to synchronous generators. Okay, so today we'll stop here. For 3-phase, just remember, you do a lot of questions in the homework, basically, to figure out when to divide or multiply by root 3. That's basically it for 3-phase, right? Conversion question in 3-phase is testing you, do you know where the root 3 goes? All right, so this root 3 comes up everywhere. So, for this week's homework, have a look at those. Next class will reinforce this power calculations again, because we need this for other things down the line. Then we'll go to synchronous generators next class. Okay, right, so I'll see you on Wednesday.
Thank you, Professor.